In this session, I'd like to explain the evolutionary path of a star. When we study the polytropic configuration of star, we discovered central pressure of a star is related to the central density of the stars using these equations. And B sub n is a really complicated equation. But if you calculate this number, B sub n, it's very weakly dependent on n. So this B sub n is almost independent of the polytropic index. So we can use this equations, relation between the P sub c, central pressure with the central density. This is a universal relation. So if we combine with the equation of state related to central pressures. Pressure is expressed a function of the density and temperatures. If we combine these two equations, you can find the temperature as a function of the densities, or density is a function of the temperatures. Then you can draw the evolutionary path on the log t, log rho planes. Then in the case of the ideal gas, we use two equations, polytropic configuration as I explained, and also equation of state. Pressure is a function of the density and temperatures. And then we can combine these two equations is equals. Then density is expressed as a function of the temperatures. Then if you take a log rho sub c, central density, log, it becomes a 3 times, this 3 comes from this one, 3 times log T sub c, central temperatures, minus 2 log m is the mass of a stars, minus 19.4. So if you increase the mass of a stars, this is going to be increasing. But you have to be careful of this negative sign. So if you increase the mass, this line is moving down. Higher mass of the stars has a lower densities. In the case of the degenerate gas, also we could use polytropic configurations of these equations and the equation of state for the degeneracy pressures of two equations. Then you can equate these two equations. Find out the central density as a function of the temperatures. But in this case, both equation does not include any temperatures. So this gonna be independent of the temperatures, but is a function of mass. So if you take a log in the both sides, is a log rho sub c is a central density, is a function of the mass of the stars. If you increase the mass of the stars, this value becomes increasing. So central density is increasing like this. Then finally, relativistic degenerate gas. We could combine the two equations for the polytropic configuration with the equation of state. Then from this equation, actually the central density, both cases is a rho sub c to the power index 4/3. So central density is cancelled out. This cancel out. So we have a unique mass of the stars. Actually, this corresponds to the Chandrasekhar mass, because the B sub 3 equal 1/4, 1 over m sub 3, 2/3. Finally, evolutionary path is expressed. Inside the zone of the ideal gas is expressed a straight line with a slope of the 3. This slope of the 3. By increasing the mass of the stars, moving to the right. In the zone of the degeneracies is independent of the temperatures. It becomes a horizontal lines is expressed. Relativistic degenerate zones is expressed is a cross of these lines. So this is exactly equal to the Chandrasekhar mass. By studying this evolutionary path, we could understand evolution of stars. Okay, this is the end of this session.